Okay, thank you. So good evening to all the participants. So today I'm going to discuss about heat pump technologies. So nowadays in India also we have started using heat pumps. So in South India also we are started using the heat pumps. So that's why I thought that we can discuss about the heat pump technologies with the students. So with that objective, as to those who don't know about me, I am Dr. Anthony Arulraj. I am the professor in Department of Mechanical Engineering. So incidentally, I am the zonal chair for History of South India. So I'll proceed with the presentation now. The overview of presentation is I'll be discussing about second law, heat pump basics, refrigeration principle, heat pump principle, and modes of operation, two modes of operation of heat pump, refrigerants used for heat pumps, types of heat pumps, and heat pump market. Okay, so all of us, we have studied about second law of thermodynamics. So most of you in this group, you would have studied about the second law of thermodynamics. So the Kelvin-Planck statement says that it is impossible for any device operating in a reversible cycle to transfer all the amount of heat given into equivalent amount of work. So some amount of heat should be rejected. Okay. So it is impossible to have a single reservoir and work produced. So that is the main core of Kelvin-Planck statement. So definitely there should be another reservoir which will be call it as the low temperature reservoir. Similarly, Clausius statement, it is impossible to transfer heat from a body at lower temperature to a body at higher temperature. Okay, so if you want to transfer heat from a body at lower temperature to a body at a higher temperature, so then we need to give external work. Okay, so otherwise it is not spontaneously possible to transfer heat body at low temperature to body high temperature. So we have discussed that these two statements are equivalent. Okay, Kelvin-Planck statement and Clausius statements both are equivalent. Okay, so if Kelvin-Planck statement is disobeyed, naturally Clausius statement also it will be disobeyed. So with that in our mind, we will go to the heat engine operation. Okay, so if you are going for a Kelvin-Planck statement, it says that, okay, so it says that if you are going for a heat engine like this, okay, so if you are considering a heat engine like this, just 1 minute, I'll take the pointer. Okay. If I'm taking a heat engine like this, so here, as per the Kelvin-Planck statement, it is impossible to transfer all the amount of heat supplied into work. So that means from here, it is not possible to transfer all delta QH into delta W. So that is not possible. So it says that this low temperature reservoir should be there. Okay, low temperature reservoir should be there. So that is the thing. So here we can see that this low temperature, it is saying that if you are having a system like where you don't have this, okay, so if you don't have a low temperature reservoir, directly all the amount of heat supplied is getting transferred into work. So that type of system is not possible. Okay, so that is what is given. So here all of you might have studied about the TS diagram. So in the TS diagram, for a heat engine that is working in the Rankine cycle, we will take one of the cycle, that is a Rankine cycle. So you know that it is impossible to work with only one high temperature only. So that you think that there is a boiler in the system. So it is not possible to work with the boiler temperature alone. Okay, with the boiler alone, it is not possible to work. Okay, so you know if I am having a TS diagram, so as per your Rankine cycle, okay, so I'll be having a system like this. So the meaning is I'll be having the high pressure, so I'll be having the low pressure also. Okay, so that is how my system will be. So you think that as per Kelvin-Planck statement, if I'm working with a single reservoir, so I'll be ending up with only one saturation temperature and one saturation pressure. So if there is one saturation pressure, that means that if there is no low pressure, that means that there is no expansion. So it means that delta P is not there. There is no expansion. If there is no expansion, it is as good as no W net. Okay, so this can be understood in this way also. Okay. And next, if I am going for okay, so here the energy balance goes like this. So if I'm having the hot source, okay, QH is equal to QC plus the W net. So that is what we have to understand. So this is QH, this is QH, and this is QC, and this value is this plus this. Okay, this plus W. So that is what we are finding. So that is the energy balance that we have to understand. This is for a heat engine. Okay, we are discussing about heat pump and refrigeration only in this concept. No harm in knowing this concept. Okay. So next, when we are going for the refrigerator, okay, so here we can apply the Kelvin Planck Clash statement. I'm sorry. So this refrigerator, so it says that it is impossible to transfer heat from a body at low temperature to body at high temperature. So that is the body at low temperature, and this is the body at high temperature. So it is impossible to transfer the heat from a body at low temperature and to the body at high temperature. But here it is happening. Okay, how this is happening? It is happening because of the work input. If suppose if this work input is not there, this is impossible. So that is what is told by Clash's statement. Okay, so that means it is impossible to transfer heat from body at low temperature to a body at high temperature, working in a reversible cycle. Okay, so if there is no work input, if work input is there, it is possible to transfer heat from body at low temperature and to body at high temperature. So that is what we have to understand. Okay, and here also, if you are having a refrigeration system, so all of you might have studied. So here also we are going to discuss about refrigeration. So in the refrigeration, if you are having a TS diagram, so you will find that you will have the system like this. Okay, so that means a reversible cycle. Okay, so the system will go like this. Is it possible to work with a single temperature or single reservoir? Is it possible? So this is low temperature reservoir, so which we call it as evaporator, and this is high temperature reservoir, which we call it as a condenser. So it is not possible. Okay, so if I'm having the evaporator temperature, okay, so then the pressure will be only one saturation pressure. So we are going to discuss in detail. So that means it is not possible to work with a single temperature. For this, I'll be having for low pressure, for low temperature, I'll be having corresponding low pressure. Similarly, for a high temperature, I'll be having a corresponding high pressure. So two pressures will be there. Okay. So it means that if it is not able to operate with single reservoir, it means that it is not possible to operate with a single pressure. Okay. So here we have to give delta P. From low pressure, we have to go to high pressure. So for that, delta P is required. So which is given by the compressor, Okay. So that is what is impossible. So that means if I want to go from low temperature to a high temperature, okay, if delta P is not given, it is not possible. So that is Clash's statement. Even if you are going for the cycle, refrigeration cycle, there also the statement is satisfied. So that is what we have to understand. Here also the energy balance here it is given by heat of condensation will be W work input. Okay, work input. Okay, so work input plus work of evaporation. Heat of evaporation. So here you will be having a low temperature heat of evaporation, and here you will be having condensation. So here you will be having work input. So the energy balance states that QE plus WI will be equal to QC. QE plus WI will be equal to QC. QC is equal to WI plus QE. So this is the energy balance here. So that we have to understand. So this is refrigerator operation. So next we can go to the heat pump operation. So in the heat pump also the same concept is there. The only difference in the heat pump is that in a refrigerator, this component will be useful. That is, the evaporator component will be useful because you want to produce cooling. In a hot place, you want to produce cooling. So this will be useful. So this will be the useful effect. Okay, when I come for heat pump, so you will maybe in a cold place. There you may be require heating. So then this will become a useful component. So that is the difference. Okay. So when this becomes a useful effect, for example, in our household air conditioning system, we are in a hot place. Okay. So here this will become indoor. So from the indoor, you will be removing the heat, and you will be pumping the heat to outside to the outdoor. Okay. So that is what you will be doing. But in a cold place, what you will do? In a cold place, exactly opposite will happen. For example, if you are living in a cold country, okay, like Europe or Russia, so their heating will be required. So then cooling is not required. So then you have to change it. This should not be the indoor. This should become the indoor. Okay, in a heat pump, this will become the indoor. That is inside the room, and this will become the outdoor. So this concept we have to understand. Okay, so in a heat pump, we put the condenser indoor, and we put the evaporator in the outdoor. From outside, the heat will be pumped inside the room continuously. Mostly heat pumps will be used in the cold countries. Okay, so European countries, Scandinavian, or United States, or in Russia. So in places like this, heat pump will be used. Okay, so there the heat pump is a necessity. Okay, in the coldest of night, so you will be requiring a lot of heating. So for that, we'll be using the heat pumps. Okay, so we will be taking the heat from the outside. Okay, so we will be taking the heat from the outside, so that is from the outdoor, and we will be pumping it indoor using the compressor. Okay, so that is what will be happening. So now I think you should understand what is the heat pump operation. So their heating is the useful operation, and this concept we can use it. Okay, so we can use it even for heating also. Suppose if you want to heat water, so you can take the heat from outside. Okay, and then you can pump it to the water. So then here you will be having water will be getting heated, so this will become a water heater. So likewise, you can for any process. Okay, so you can use heat for heating water, for heating air, for any other place you can use. So that becomes a heat pump. Okay, so in heat pump is like a heater. Okay, uh, how you compare a heat pump with the heater? So heat pump will be more efficient than a heater. So that we will see it in in our subsequent slides. So now we have discussed about the second law of thermodynamics, that is Kelvin Planck statement we have discussed. Then we have discussed about Clausius statement also. Okay. So from there we have to proceed to the next. Okay. So that is we will go to the concept of heat pump. So for understanding the concept of heat pump, so we have to understand the concept of refrigeration, because heat pump and refrigeration, it will go hand in hand. Okay, so same device only, our place of utility will become different. So here you can understand. So here also this is a refrigerator, and this is a heat pump. This is heat pump, and this is a refrigerator. Same device only. Okay, so it is removing heat, and it is giving out to the environment. So this I call it as refrigerator. In a household refrigerator, so there is a confined space. Okay, that is a refrigerated cabinet. From there we are removing the heat, and we are sending it to the, giving it to the surrounding. Or in other words, suppose if you are having an air conditioner in a closed room, you are removing the heat and you are leaving it outside through the condenser. So here this will become the useful effect. When I'm going to the cold place, okay, like Europe, so there what I'm doing, I'm using the same equipment. Now I want to heat the house. So what I'm doing, so here only you will be having hotness. In the condenser only you will be having hotness. So I'm putting the condenser inside the room. Okay. So this is the useful effect. Okay. So and this I'm removing I'm putting my evaporator outside. So when I put the evaporator outside, it will take the heat from the surrounding, and it will be pumping it to the house. Okay, so that is the concept we have to understand. It will take the heat from the surrounding, and it will pump to the house. So for that, it is the heat is blowing. It is moving from a low temperature reservoir to high temperature reservoir. This cannot happen with without W net. So that we have to understand. So to conclude, we have to understand that in a refrigerator, the refrigerated space will becomes a useful effect. In a heat pump, the condenser becomes a useful place. Okay, so we put the condenser inside the house. Okay, or we put the condenser inside the water for heating it. Okay, so that is how we have to understand. Okay, so now we have a concept called as coefficient of performance, which is like efficiency in a heat engine. Okay, so what is the coefficient of performance? It is a useful effect by work input. So in the case of a refrigerator, the useful effect is the amount of heat removed. So this is a refrigerator. So this is a refrigerator cabinet. So how much heat is removed from the refrigerator cabinet? So that is QL. This is QL. So QL divided by W net. Okay. So W net is what we give it here. So the QL divided by W net. So that will become the coefficient of performance of the refrigerator. Okay. So next is we'll be having we can apply the same concept to heat pump. So there the useful effect is the heat of condensation or heat rejected to the condenser. Okay, so that the heat of condensation will be pumped inside the house. So the useful effect will be QH divided by W net. So this is W net. Okay, so QH divided by W net. So that is what I have it here. Okay, so now you know this energy balance. Okay, so you know this energy balance already. I told you. So QH or the heat of condenser. Okay, so I can write QH is equal to QL plus W net. W are work input. So here you can see the heat is flowing from the refrigerator to the our system. So this plus the W net will be equal to QH. So that is what I have written here. It's very simple. Or if you want to understand better, you can write QC is equal to QE plus W. So the meaning is the heat of condensation is equal to heat of evaporation plus W. So W plus QE. So this plus this will be equal to QC, heat of condensation. Okay. Now a simple exercise, you can divide throughout by W. So when I divide throughout by W, what I get? QC by W, QE by W, W by W. So you know that QC by W or QH by W. So that will be the coefficient of performance of heat pump. Okay. So that will be coefficient of performance of heat pump, and this will be equal to QE by W. So that is the coefficient of performance of the refrigerator. So that we know. Just now we have seen that, and plus 1. So what we have to understand from this, so at the always the coefficient of performance of the heat pump, it will be greater than the coefficient of performance of the refrigerator. So that is the first concept we have to understand. So what is the meaning of that? So if you are giving 1 kilowatt to the refrigerator, okay, suppose you consider the coefficient of performance of your refrigerator as 3. Suppose if you are giving 1 kilowatt to the refrigerator, so you will be getting 3 kilowatt of cooling. Okay, but the same if the heat pump is having a coefficient, or you think that if your equipment is having the coefficient of performance 3, that is so then it means that your COP of refrigerator is 3 plus 1. That means you'll be having 4 as the COP of the heat pump. So if the COP of heat pump is 4, what is the meaning? If we give 1 kilowatt of work input to the compressor, so you will be getting 4 kilowatt. Okay, so you will be getting, so you will be getting 4 kilowatt of heat. So that is the advantage. So you may be thinking it is not balancing the energy. So it's not about energy balance. Okay, so our place of utility becomes different. Okay, so this becomes our useful effect. That means this becomes whatever the heat we are dumping outside, that becomes our useful effect. So that means this divided by the work input, that is 1 kilowatt. So this becomes 4 kilowatt, and this becomes 1 kilowatt. Okay, so because of that, 4 divided by 1. Okay, so my my energy efficiency is higher. Okay, Again, how I told that we can compare the heat pump with a heater. So when I'm using a heater, okay, so if I'm giving a 1 kilowatt to a heater, okay, so when I'm giving 1 kilowatt to a heater, so then it will give me heat when it is if you're using a electric heater. So then if I'm giving 1 kilowatt because of the efficiency of heating, so it may be giving you around 0.95 kilowatt of heat, or it may be zero point 0.9 depending on the case, zero point 0.9 kilowatt of heating. I give 1 kilowatt, I get 0.9 kilowatt. But to the heat pump, if I give the same 1 kilowatt, okay, so it will be giving 4 kilowatt. So that means uh, this is the best option. That means heat pump is the best option for heating from the energy efficiency point of view. Okay, so that's why in the Western countries always they will advise to go for heat pump only. But in our place, we are using electric heater. So in Western countries, using electric heater it is considered like a crime. Okay, but in our place, still we are using electric heater. So electric heater can be used in some intricate places, but not in all the places. So in all the places, it should be advised to use heat pumps only. Because again, I'm trying to tell, if you give 1 kilowatt to the heat pump, it will maybe giving a 4 kilowatt of heating. If I am giving 1 kilowatt to a electric heater, it will be giving 0.95 kilowatt only, or almost 1 kilowatt we can say, if it is 100% efficient. So 1 kilowatt it may give. Okay, so compare where is 4 kilowatt and where is 1 kilowatt. So that is the advantage we are having when we are going for a heat pump. So hope you have understanding. So it has a higher energy efficiency. So you should not think that it is not satisfying the energy balance. So here the energy balance is this one. This we have to understand. That is heat of condensation will be equal to heat of evaporation plus work input. Okay, energy is balanced. Absolutely, there is no problem. Here also 4 kilo, because this is 3 kilowatt and this is 1 kilowatt, and here it is we are having 4 kilowatt. Energy is balanced. But the way we are interpreting things, okay, so we are taking ratio of this. So the ratio of this will become so 4 by 1. Okay, then it becomes 4. If you are taking the correct efficiency, it will be W by QH. So it will be 1 by 4, 25. Okay, so that we have to understand. Okay, um, so this is the advantage of having the heat pump. So with that, we can go to understand how the heat pump is working. For understanding how the heat pump is working, so first we can understand how the refrigeration system is working. So you know that we'll be having various components in a refrigerator. So in a refrigerator, okay. So in a refrigerator, so we will be having the evaporator. So in the evaporator, the heat will be removed. So we'll be having the refrigerant. So at the inlet of the evaporator, you will be having liquid refrigerant. So the liquid refrigerant will be evaporating. So it will be converted into vapor. So the vapor will be compressed in the compressor. So that's why the name vapor compressor. Okay, vapor compression refrigeration system. So the vapor is compressed. So from there, the compressed vapors at high temperature will be entering the condenser. There we will be removing the heat from the condenser. Okay, so we will be removing the heat from the condenser by using an air-cooled condenser or water-cooled condenser. Okay, so when after the heat is removed or heat of condensation is removed, so the high temperature vapors will become low temperature liquid. So the low temperature liquid will be entering here. Okay, so low temperature liquid will be entering here, and continuously it will be producing the refrigeration. So if you ask me why we are going for this system, so I would say that we are going for this type of system basically for regenerating the refrigerant. So the meaning is even if you are having an evaporator like this, okay, so this evaporation can be produced by having some volatile substance in your hand. Okay, so if you are making the volatile substance to evaporate, so it will produce the cooling. So for example, if you put alcohol in your hand or refrigerant in your hand, so it will evaporate and it will produce cooling. Okay, so that means continuously cooling can be generated by evaporating the volatile fluid. But if you are evaporating the volatile fluid, then you are making a costly refrigerant to evaporate. It will escape to the atmosphere. We don't want to refrigerant to escape to the atmosphere, because you know that 1 kg of refrigerant, it will maybe around 750 rupees. Okay, so you don't want to lose that refrigerant continuously for producing cooling. So the best way is you have to regenerate the refrigerant. For regenerating the refrigerant only, these components are required. So that is the compressor, condenser, and the expansion valve are required. More about that we will discuss subsequently. So now we can go through the process. In the evaporator, the liquid refrigerant will be entering inside, or I cannot. So two-phase refrigerant will be entering inside. So it will be evaporating. So at the end of evaporation, so it will become saturated vapor. So already I told you. So the vapor will be entering the refrigerant. So I told that when the main purpose of the compressor is to increase the pressure. So from this is low pressure. So from the low pressure it will go to the high pressure. Okay, so that low pressure it will go to the high pressure. And after that, I told that it will be rejecting heat to the surrounding. So here this will be rejecting heat to the surrounding. As it is rejecting heat of condensation, so it will become a saturated liquid. So the saturated liquid will be expanding in the expansion valve. So 3 to 4 process is the expansion process. So after the expansion, it will become low temperature liquid. Okay. So before expansion, it will be a high temperature liquid. After expansion, it will become low temperature liquid. So because of that, this system is working. So it is continuously it will be removing heat from the evaporator, and continuously it will be dumping heat to the surrounding from the condenser. So that's how this system will be working. Okay. And you know that this is a TS diagram. So this is a temperature, and this is entropy diagram. So here you'll be having high temperature, and here I will be having low temperature. Already I told you, so you cannot operate with one temperature only. That is a single reservoir alone, you cannot operate. So this is high temperature means the corresponding pressure. Okay, the corresponding pressure line will be going like this. So this is high pressure line, and here this is a low temperature. The corresponding pressure line will be low pressure line. So this is low pressure line. Okay, so I told that it is not possible to operate on a single pressure. Okay, so two pressures are required, or two temperatures are required, because if for one low pressure, corresponding saturation temperature is this one. Okay, so this is a low temperature. For high pressure, the corresponding saturation temperature will be TH. So two temperatures are required. Okay, so that concept we should understand. The same thing we can present it in a pH diagram. Okay, so I can, if I have to draw this in the pH plane, so here you can see that. So this will be the high pressure line, and this will be the low pressure line. Okay, so you know that this is a constant pressure process. So whatever the cycle I had shown previously, so this is constant pressure process. So in this plane of the constant pressure process, it will be going like this. From here, it will be going like this. Similarly, the constant pressure process, it will be going like this. So all these concepts, I think you would have studied in your lower classes. But when I come to pH diagram, so it will be appearing as constant pressure line. So this will be the constant pressure line. So let me call this as high pressure line, and this will be the constant pressure. This will be the low pressure line. Okay, for going from low pressure to high pressure, we require the component called as a compressor. Okay, so that is what we have understood. And from coming from a high pressure to low pressure, we require a expansion valve. Okay, so here 3 to 4, it is expansion process. So you know that expansion process is an isenthalpic process. Okay, so that is the concept what we have to understand. And okay, so now we'll try to understand this concept still further. We'll go one step further to understand it. Already I told you, I have this is a R134a. Okay, so this is R134a chart. Okay, so this is R134a chart, and in this we have basically in a refrigerator we'll be having 4 processes. Even in the heat pump also we'll be having 4 processes only. Okay, so here I'll be having the evaporation process. From here to here I'll be having the evaporation process. From here to this point, okay, so I'll be having the compression process. From the compression 2 to 3, I'll be having the condensation process, and 3 to 4, I'll be having the expansion process. Okay, fine. So now, as I told already, so we can try to understand. Okay, so from the refrigeration chart, so here the evaporator temperature for this it is minus 20 degrees centigrade. Okay, so here the evaporator temperature is minus 20 degrees centigrade from the R134a chart, and the pressure also you can identify. So the pressure is here, it is 100 kilopascal, and here it is 200 kilopascal. So we can think that it is approximately around 150 kilopascal. So 150 kilopascal, I can call it as 1.5 bar. Okay, so here it is 1.5 bar, and now the evaporation is taking place here. Okay, so when I check that if you are taking the refrigerant 134a, and if you are trying to evaporate it, so what will happen? It will evaporate at minus 20 degrees centigrade. Okay, so at atmospheric pressure. Okay, so at atmospheric pressure, it will be operating at a still lower temperature. Suppose if you are keeping it open, okay, so still it may be evaporating at minus 25 degrees, for example. Okay, now since you are having 1.5 bar in the evaporator, it is evaporating like this. So think that you are keeping it, just opening it in the atmosphere, keeping it open in the atmosphere. You are taking some refrigerant in your hand, you are leaving it in the atmosphere. What will happen? Your hand will get cooled. Okay, so when your hand is getting cooled, it is removing heat from your hand. So that is why your hand is getting cooled. Okay, and also you will find that it will be evaporating. Your R134a, it will be evaporating. The same thing will happen in petrol also. You put some petrol in your hand, it will try to evaporate. So if petrol is evaporating, so that means it is cooling your hand. So cooling process is taking place. So that is what is happening here. Okay. Now I have asked one question. So that means, is it possible to reject the heat at the same temperature? Okay. So practically we will approach this problem. So is it possible to reject the heat at the same temperature? So now think that you are inside the room. Okay, so that means this is an air conditioner system, or you think that some cooling system is there. Okay, because air conditioner will not have minus 20 degrees in the operator. So you have a cooling system. So inside the refrigerator cabinet, what will be the temperature? So inside the refrigerator cabinet, the temperature may be around, in the beginning it may be around 30 degrees centigrade. So gradually the temperature will be decreasing. So initially the cabinet is 30 degrees centigrade, and your evaporator is at minus 25 or minus 20, whatever the case may be. Okay. So now you know that heat will always flow from 30 degrees to minus 20 degrees. Naturally, the flow will be taking place. Okay. So that means it will remove the heat from the room or from the refrigerator space naturally. Okay. Now you want to dump this heat. Okay. Now you want to dump this heat to the surrounding through the condenser. Okay. Suppose if I am having, if I am at the same pressure, is it possible to dump this heat? Anyone? If I am having it at the same 1.5 bar, I want to dump this heat to the atmosphere. Is it possible? Anyone can unmute yourself and answer. Okay, so I will answer you. So it is not possible. Why it is not possible? Because already your atmosphere is at 30 degrees centigrade. Okay, and you are removing heat from that at 30 degrees centigrade. Okay, so now if your refrigerant is at minus 20 or minus 25 degrees centigrade, it can naturally flow. Okay, now if you want to dump the same heat to the surrounding at 30 degrees, okay, so that is not possible. From minus 25, the heat cannot flow to 30 degrees. Is it clear? So from minus 20 degrees, heat cannot flow to 30 degrees. Now I want to increase the, somehow I want to dump the heat to the surrounding. So what is that I can do? I have to raise the temperature of the refrigerant so that I can dump the heat to the surrounding. So how I can increase the temperature of the refrigerant? So the only way by which I can increase the temperature of the refrigerant by the properties of pure substance, we can understand that if I increase the pressure, the saturation temperature will increase. So when I increase the pressure, the saturation temperature also it will be increasing. So what I am doing initially, I am increasing the pressure, so I am getting 0 degrees centigrade. At what maybe around 3 bar, I am getting 0 degrees centigrade. But I cannot dump the heat to the surrounding even at 0 degrees centigrade also, because you know that from 0 degrees heat will not flow to 30 degrees centigrade. Again, I am increasing the pressure. Okay, so now the temperature is around 20 degrees centigrade. The pressure is around 5 bar. Okay, 5 bar or 5.5 bar, 5.5 bar. The temperature is again 20 degrees centigrade. Now also the heat cannot flow from 20 degrees to 30 degrees. So further I am increasing the pressure. So when I am increasing the pressure, okay, now the pressure is 10 bar. Okay, now the corresponding saturation temperature is 40 degrees centigrade. Now you can understand from 40 degrees centigrade, the heat can flow easily to 30 degrees surrounding. So now the surrounding is at 30 degrees centigrade. If you want the heat to flow from the refrigerant to the surrounding, you have to raise the temperature up to 40 degrees or 50 degrees. So for that, what you have to do, as such, you cannot raise the temperature. You have to raise the pressure. Then only the temperature will be increasing. So there comes the requirement for increasing the pressure. Okay, so here the pressure is 10 bar. Maybe if you increase the pressure to 15 bar, for example, here the pressure will be around 15 bar. So there you may be getting the temperature of around 55 degrees centigrade, which will be 50 degrees centigrade, for example, which will be ideal. Okay, even in summer also it will be able to dump the heat to the surrounding. Okay, for us, you know that our surrounding temperature will go up to 40 degrees or 43 degrees during summer. So in that case, you have to raise your refrigerant temperature to 50 degrees. Then only the heat will flow. So that is the concept by which we are increasing the pressure of the refrigerant. Why we are increasing the pressure of the refrigerant? So only if I increase the pressure of the refrigerant, then heat will naturally flow from the refrigerant to the surrounding. Otherwise, that will not happen. So now you can understand the concept. I told you in the beginning itself. So you should have two temperatures. Then only you can operate a heat engine. This is reversible heat engine. It cannot be operated at a single temperature, because I told now, if you're operating at a single temperature, it will flow from indoor to the refrigerant. From the refrigerant, it will not flow to the surrounding. Okay. So if you want the heat to flow from the indoor to the surrounding, I have to increase the temperature. If I have to increase the temperature, I have to increase the pressure. So for that only we are using the compressor. So you should understand why we are using the compressor. If compressor is not there, if pressure is not raised, then you cannot achieve the temperature of around 40 to 50 degrees in the condenser. Then if you are raising the pressure, then naturally from that temperature, the heat will be flowing from the refrigerant to the surrounding. Okay, so now you will understand the importance of the compressor. Okay, similarly, you may be thinking by knowing this, you may be thinking that the compressor is an important component of the refrigeration system, but that is not so. Okay, so I would say that your expansion valve is equally important, because why, you know, at the upstream of the expansion valve, there will be high pressure. Okay, so that means the 10 bar, 15 bar will be there. At the downstream of the expansion valve, you will be having a low pressure. So here we are finding the low pressure of around 1.5 bar. So this pressure difference, it is maintained. Okay, so this is 15 bar and this is 1.5 bar. This pressure difference, it is maintained by the expansion valve only. Suppose if this expansion valve is not there, what will happen? So you will be having the liquid refrigerant. After condensation, liquid refrigerant will be there. Okay, what will happen? That liquid refrigerant will be at a high pressure only. So at a high pressure, again, it cannot evaporate. Only at a low pressure, low temperature, it can evaporate. So separating this high pressure to low pressure. So this component is also equally important. So that we have to understand. Okay. So I'll show you a small video. So which have been prepared by me and one of the student, your senior student. So for you to okay, 1 minute. So now we will go through this video. Then again we will go back to our discussion. So you can access to this video. Okay.
We have this entire misunderstanding of what Darwin really meant when he said survival of the fittest.
Okay. So if you are putting a refrigerant in your hand, so that's what I told already. It will try to evaporate. So we are putting that refrigerant in the evaporator solid. If you are allowing the refrigerant just like that, you will lose the costly refrigerant. So we want to recover the refrigerant. So at the same pressure, you cannot reject the heat. So for rejecting the heat, the pressure should be greater than atmospheric pressure. So for that, compressor is required. For rising the pressure, compressor is required. Okay. So here you can see that we are going from low pressure to high pressure. And we have to separate this high pressure and low pressure. So that is very important. So otherwise, what will happen? So this will be working like a pump. Okay, this will be working like a pump. Evaporation will not be taking place. Okay. So expansion valve is key in separating these two components. That we have to understand. So now you can understand. So expansion valve separates the high pressure to low pressure. So that is very important. You have to understand this. So pressure difference is important. Okay. 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 So we understand that the pressure difference is important. Okay. So pressure difference is important. So that we have to know. Okay. And one more component thing you have to understand about the. So now we have understood the concept of the refrigeration. So what about the heat pump? So what is the methodology for the heat pump? So here I say that there is no much difference between the refrigeration and the air condition. Refrigerator and the heat pump. So in the heat pump, the only difference is this becomes a useful portion. So that is the condensation. So this part becomes useful. Okay, and this part will become the evaporator. So you know that the energy balance for the heat pump. So it goes like this. Already we have written the energy balance for the heat pump like this. So I have heat of condenser will be equal to heat of evaporator plus W. So that is what we are having. So what we have to understand from this evaporator, already I told, for example, this will be 3 kilowatt and this will be 1 kilowatt, and this will be 4 kilowatt. So this concept also you have to understand, the capacity also. Why I am stressing here, because 3 kilowatt, if you are having the cooling coil, so you will be having copper pipes with the fins. Okay, so you will be designing using this formula UA-LMTD. So this is heat exchanger design. So this will be Q will be equal to Q of evaporator equal to UA-LMTD. So this capacity will be 3 kilowatt. So corresponding to 3 kilowatt, if you are designing for using this formula UA-LMTD, so this capacity or the length of the coil will be smaller in the evaporator. If I am going for the same design with the condenser, okay, so QC will be again equal to UA-LMTD. So with this formula, if I am going to design for the condenser, so QC will be equal to 4 kilowatt. So this will be equal to 4 kilowatt. So when based on this, if I'm calculating the area, so you know that the area will be n into pi dl, that is the length of the pipe. So the number of pipes will be more in the condenser. This is natural. Even if you are taking your household refrigerator or the air conditioner, you will always find the number of coils required for the evaporator will be smaller. The number of coils required for the condenser will be more compared to the evaporator. So that means in a heat pump, if I am trying to put a heat pump in the indoor, there the number of the length of the coil required will be more. Okay, so here the length of the coil will be more, and in the evaporator the length of the coil required will be less. Okay, why I am telling this, because there is a concept by which you can use this heat pump both in summer as well as winter. Think about a place like Delhi. In Delhi, the summer will be very hot and the winter will be very cold. So if you want to tackle this, what you can use it is you can go for a same equipment. You can use it as a refrigerator as well as air conditioner as well as the heat pump. Okay, so what you have to do it, so you have to change the evaporator and the condenser. So that means indoor unit you have to change it as a evaporator during summer, and you have to change it as a condenser during winter. So that means it will be working like a heat pump during winter, and it will be working like a evaporator in the during summer. So when you go for this concept, it will create problem, because when you are using it as a condenser, okay, so when you are using it as a condenser, so then here the coil required will be more. That is, the number of coils required will be more. When we are using it as an evaporator, number of coils required will be less. Okay, so that is one important problem that we have to understand. So for overcoming that, okay, so what we have to do is that we should have some special arrangement for matching the coil, as well as you should have some special arrangement for reversing the flow, some mechanism to reversing the flow. So usually we'll be using a three-way mechanism for reversing the flow in a heat pump. So let us discuss about how this same refrigeration system or the heat pump system can be used as for heating as well as cooling mode. So I can call it as a heat pump, which is used in the heating mode during winter and cooling mode during summer. So with that, yeah, so this is the thing. So here you can see that this is the compressor. Okay, so this is the compressor, and from the compressor, now the heat pump is used in the heating mode. So if it is heating mode, so that means your condenser should be in the indoor. So now here you can see this is indoor, and this is outdoor. That you have to understand. This is given here. Okay, that is given very. So this is indoor, and so that means from the that from the compressor you will be getting the hot gas. That hot gas should go to the indoor. Okay, so now we are having a three-way valve. Okay, so now this valve is diverting. It is closing these two, and it is making the refrigerant vapors or compressed high temperature, high pressure vapors to go to the indoor. So there you will be having heating inside. You will be having heating inside, and condensation will take place, and after that it will pass through the expansion valve, from there it will go to the outdoor. Okay, so there in the outdoor, you will be having evaporation will be taking place. Okay, so evaporation will be taking place. Okay, so you know that after condenser you will be having a evaporator, expansion wall and the evaporator. So evaporation will be taking place. So in short, what is happening? So from here, okay, so from here I'm having the evaporated heat. Okay, so in the evaporated from the heat from the atmosphere, it is entering into the into the cooling coil or the evaporator coil. So from there, it adds the compression work. So that is given, heat of condensation is given into the indoor space. So that is how the heat pump is working in the heating mode. The same heat pump can be used in the cooling mode. So this will remain as indoor and this will remain as outdoor only. So if you want to work the same heat pump in the cooling mode, what you have to do? So indoor should become evaporator and outdoor should become condenser. So that means the hot gas from the compressor, it should go outside. So that is outdoor. So that is the system what we will be seeing next. So now here you can see this is as discussed previously, this is indoor, okay, and this will be outdoor, okay. So now the system is working in cooling mode. So that means the hot gas from the compressor, it should go outdoor, okay. So there condensation, it will be working like a condenser. There the condensation will be taking place, and after that it will be expanding in the expansion coil. And after that, you know that low temperature liquid will be operating in the evaporator. Okay, so indoor you will be having evaporation here. Okay, so you will be having a evaporation here. Okay, so in the outdoor condensation will be taking place. Okay, so this will be working in the summer. This is summer operation. You think that a place like Delhi during summer this will be working. And also you can see that this three-way valve, what it is doing, it is closing this valve and it is opening this valve. So that thus with the same air conditioning system, you can operate it both in cooling mode as well as the heating mode. Okay, so that means you can call it as a heat pump working in heating mode or cooling mode, or you can call it as a air conditioner working in heating mode or cooling mode, whatever it. So it works both as heat pump as well as the air conditioner. So it works as a heat pump during winter and it will be working as a air conditioner during summer. So this concept we should understand. Okay. And the next thing is what are all the different types of refrigerants used in the heat pump system. So all of us we will be knowing that there are different categories of refrigerants. So nowadays we are using zeotropes. So zeotropes are a mixture of refrigerants. So, but it will not be having the same evaporation temperature. Okay, so since we are mixing two refrigerants, it will be having a range of evaporation temperature, and this evaporation will take place at a fixed temperature only. Okay, so it will not be taking place in the fixed temperature. It will be taking place in a range of temperatures. Okay, and we will be using azeotropes also. In the azeotropes, you will be having a uniform temperature. That means constant temperature evaporation will be taking place. So that we call it as R400 500 series, and R600 series also it is used as refrigerants. So all of you will be knowing that R600 series are mostly organic hydrocarbons. Okay, mostly they are fuels like propane, butane, hexane. All these things will be coming under R600 series, and we can use inorganic refrigerants also. So inorganic refrigerants like R700, that is ammonia, can be used as the refrigerant. Okay. So this can be used as a refrigerant for the heat pump. Okay, so all these types of refrigerants are used in the heat pumps. Specifically, we can see a few refrigerants. R134 type A, it's a common refrigerant which is used. So it has a very good efficiency compared to R407C and R410A. Both are zeotropes. I'm sorry, both are zeotropes. So it will be having a lower efficiency compared to ammonia refrigerants. Okay, this R134A has a better efficiency compared to R407C and 410A, but lower efficiency compared to ammonia. Okay, and if I go for R407C and R410A, So we have seen this are zeotropes, and having a variety of a range of boiling temperature. So they are widely used. Okay, so under the supercritical temperature will be 71 degrees centigrade. So it is obvious for a refrigerant, the supercritical temperature will be around 71 only, and efficiency will be higher, but investment is low compared to R134. Okay, so investment will be lesser, but for R134a the investment will be more. Next, when I am going for R600 series, in the R600 series, we will be having butane and isobutane. These can be used as a refrigerant. So these are commonly used refrigerants. So other refrigerants also can be used, like propane and other things. But butane and isobutane will have superior performance compared to other R600 series. Okay. And already I told that these are all fuels, hydrocarbon fuels. So it will be having fire explosive property. So we have to take care in the installation. Okay, and R717, that is ammonia, it has a very superior characteristics. Okay, so just 1 minute. Okay, just 1 minute. Just 1 minute. I'll join. Okay. Yeah, we'll continue with our discussion. So, am I audible to everyone?
Yes, sir.
Yes, sir.
So ammonia is a superior refrigerant, okay, compared to other types. So it will be having a highest efficiency, and it is a natural refrigerant. Okay, so it will not have any global warming potential or greenhouse effect. Okay, but only problem is ammonia is inflammable and toxic. Okay, so otherwise ammonia is very good, but even if it is toxic, you can easily understand. You can usually feel if ammonia is leaking, okay, because of its order. So you can easily understand that if ammonia is leaking or not. Okay, but the problem is it is inflammable and toxic. Okay, so that's why it's not. But it is a very superior refrigerant. Okay. Okay, so these are all the refrigerants which can be used in the heat pumps. And what are all the different types of heat pumps? Okay, so we have air-to-air heat pumps, air-to-water heat pumps, ground source heat pumps, and water source heat pumps. Okay, what is air-to-air heat pumps? So if the outdoor is also a air-to-air heat exchanger, and indoor also. Okay, it is air-to-air heat exchanger. So the best way to explain this is, so you are removing the heat from the outdoor, and you are heat from the air from the outdoor, and you are pumping the heat to the air, indoor air. So that means from the outdoor air you are removing the heat, and you are transferring the heat to the indoor air. So that is called as air-to-air heat pump. So this is almost like our air conditioners. So what we are doing in our air conditioners, we are removing the heat from the indoor air, and we are giving it to the outdoor air. So there also it is air-to-air only. But here, if you are removing the heat from the outdoor air and giving it to the indoor air, so then it is called as air-to-air heat pumps. Okay. So here you can see that this is indoor air and this is outdoor air. Okay. So this is outdoor air and you have compressor. So it's a two-way system. Like you can have a reversing valve and you can have two-way operation, like what I told already. But what we have to understand is that air-to-air heat pumps. Okay. So we will be removing the air from the outdoor, and we will be we will be removing the heat from air outdoor, and we will be pumping that heat to the indoor air. So this is called as air-to-air heat pump. And air-to-water heat pumps. So if you are removing the heat from the outdoor air and you are passing that heat to the indoor water, or I can say if you are passing that heat to water, then now the heat is transferred from the air to water. That is, from outdoor water, heat is transferred to, from the outdoor air, heat is transferred to the water. So that is called air to water heat pumps. So you may ask where this thing is used. So mostly this is used in water heating purpose. So you think about hill station like Ooty, Kodaikanal and North India, all Kashmir and other places. So there you may have some cold places where you may requiring a hot water. So for that, what you can do is you can remove, you can use that air to water heat pump. So this will replace your electric heater. So already I told you, if you are using electric heater, it will not be energy efficient. In fact, you should not use electric heater for water heating purpose. So you have to go for heat pump. So for that, what you can do is you can take the heat from the outdoor and you can pass that heat to the indoor, or I can say water. So from the outdoor, you are taking the heat from the air and you are passing that heat to the water. So that is called air to water heat pump. Okay. So more about this, I think we will discuss subsequently, or I will show you a video. Okay. And another way of operating is the ground to air heat pump. Okay. So there will be, as like I told, in winter places, so the surrounding will be at a very low temperature. For example, it may go up to -20 or -30 degrees also. Sometimes in Russia and all the temperature will be very low. Okay. So if the surrounding is at -20 degrees and you cannot think of taking the heat from the surrounding and pumping it inside. So in that case, what you can see is maybe your surrounding will be at a very low temperature, but your ground will be at a very high temperature compared to the surrounding. So what you can do is in places like Russia, so you can take the heat from the ground and that you can pump it into the room. Okay, so we know that in coldest of night in Russia and all, you will be having the surrounding will be at a very low temperature, -25, -20, -15. So that will be the order of the temperature. So instead of taking the heat from the surrounding air or surrounding, so what you can do is you can take the heat from the ground. So the ground will be hotter compared to this. So from the ground you can take the heat and you can pump that heat to the indoor space, so that indoor will be comfortable. So that is one form. So that is ground to air heat pumps. So this is very common in cold countries like Canada and Russia. This concept is very common. Ground to air heat pump. Okay. So here you are having ground. Okay. So from that we are removing the heat and using your heat pump system, we are pumping it to the indoor air. So that means for heating the indoor, we are using that system. Okay. So it is all from where you are taking the heat and where you are pumping the heat. So that's what we call it as a heat pump. So here we are taking the heat from the ground, we are giving it to the indoor air. So the next one is water to air heat pump. That is last one, water source heat pump. So in places where you are not finding a very good source for heat, if your water is heat, then you can take the water as your heat source. And you can remove the heat from the water. You can remove the heat from the water and you can pump it to the condenser, which is there at the indoor. Okay. So in that process, okay, so you can easily pump the heat from the water to the indoor space. So that is what we call it as water to air. But here a water source heat pump. That means you are having that should be a water source. It will be at a relatively high temperature. So that can be a lake, or it can be a pond, or it can be a river, or it can be a sea also. So you can use these water bodies for taking the heat, and that heat you can pump it to the indoor space. So that is what we have to understand. Okay. And the thing is, what about the heat pump market? So the heat pump market, so you may be thinking that a heat pump I'm not come across, but you can think about the market for heat pumps. So Mitsubishi Electrical, it is having a market revenue annual revenue of around $40.35 billion. Okay. Daikin, $23.06 billion. Carrier Corporation, so 18.61 billion. And the Johnson Controls, okay, so 14.79 billion. So Danfoss 6.94, Ingersoll Rand, so it is 2.45. So you should understand that I want to convey you that it is not a small market. It may be a small market in our India, but even in our place also, in few places this market is picking up. So that's why I want to pass on this concept of heat pump to all the students. So you have to learn about the heat pumps and you have to get employed in some heat pump companies. So in that only, in mind only, I have done this. And just we can go